Hi, my name is Yutao, and I will be presenting Planning Paths Through Unknown Space by Imagining What Lies Therein. This work presents a novel framework for informed path planning in occlusion-heavy scenes by leveraging an image inpainting network. In this outdoor image from the Kitty dataset, there are structures such as hedges, buildings, and fences which obstruct sensor measurements and produce a map with unknown spaces. The goal of our paper is to present a framework for more informed planning in environments such as this one. Traditional approaches generally make the optimistic assumption that occluded space is free, although some approaches simply do not plan paths through unknown spaces. However, our intuition tells us that a predictive model of what occupies the occluded space should produce better planning results. Recently, learning-based approaches have been used with some success. These approaches, however, generally have been limited to indoor environments. Our framework works as follows. Given an initial semantically labeled point cloud, which can be readily obtained through computer vision or LiDAR classification techniques, a bird's eye view or BEV of the point cloud is projected. This bird's eye view image is then filled in using a learned image inpainting network. The inpainted image is then used as an obstacle map for navigation. The point cloud is projected to the bird's eye view to allow for the inpainting of occluded space not visible from the initial viewpoint. To derive the dataset for training the network, we modified the data from the semantic kitty dataset. On the left of the image below is a semantically annotated single LiDAR scan. On the right is a semantically annotated point cloud of all LiDAR scans which pass through the same area concatenated together. Our dataset provides bird's eye view rendered images of the single LiDAR scans along with the ground truth filled in point cloud from the concatenated scans. The mask indicates which pixels are known in black and unknown in white. The goal of inpainting is to fill in the unknown pixels with a learned network for more informed path planning. Here are some qualitative results for the inpainting. Odd rows correspond to distinct images. Even rows shows obstacle maps corresponding to the images above. The inpainting performs well for LiDAR scans. It is able to predict unseen obstacles well. The inpainting did not perform as well for stereo point clouds due to less accurate depth and because the network is only trained on data from the LiDAR scans. Quantitative results for the inpainting are provided in the paper. We evaluate the performance of a planner using our inpainted obstacle map compared to a typical optimistic planner which assumes unknown space is free. An A-star planner is used, although any generic off-the-shelf planner is compatible with our framework. Here is a bar plot comparing average path lengths for the optimistic baseline, our framework, and the ground truth map. Error bars of 1 standard deviation are displayed. Our inpainted obstacle map outperformed the optimistic baseline for all experiments except in the most simple image where there were few obstacles to predict. Here is a comparison of the number of replans between the optimistic baseline and our planner. Results for the ground truth are not shown since no replanning is necessary. Our inpainted obstacle map requires less replans for all scenarios, meaning the robot runs into less dead ends and is more efficient in reaching the goal. Our framework also works better on more complex scenes. Here's a video example comparison between the optimistic baseline and our framework. The goal is located in the top right of each image. Pay attention to how in the optimistic baseline example, the planner must replan several times online as it runs into obstacles, whereas for the inpainted obstacle map, the planner is able to navigate directly to the goal, as some occluded obstacles were filled in by the inpainting network, increasing efficiency and reducing the number of replans needed. In summary, we presented a novel framework for planning in occlusion-heavy environments by leveraging inpainting networks as a predictive model of unknown spaces. We demonstrate significant improvement of the baseline of an optimistic planner in terms of path length and replans done. We also provide a dataset for training inpainting networks for planning in urban outdoor environments. This work is sponsored by the Office of Naval Research. We would also like to thank the reviewers for their helpful comments. Please refer to our paper for more detailed methods, analysis, and full results, and check out our work at the link listed below.